when working on the object level, the structure level algorithms are much easier than the object level algorithms. Most of the difficulties and most of the errors in user content come up at the object level. So this in particular describes what the parsing and the checking do. So the idea is you have some input, say a constant declaration a colon uppercase A equal t, and now parsing and checking will operate on this constant. So first of all, we have two terms occurring in this declaration, and the parser will treat them both the same way. It will build a parsing unit containing the current context that will in particular contain the current theory and the actual string that has to be parsed. That is sent to the parser returns a parse result which contains three components. Well, I erased one for simplicity, so let's say two components. The context u of unknown metavariables and the term t, which is the result of parsing this lowercase term t here. And the invariant is that t is going to be a term in the context c, comma u. Meaning, anyway, t may refer to all the variables from the context in which parsing happened, that's obvious. But also t may contain all these new metavariables in u, which are introduced by the parser and then returned together with the parse result. What the parser does is, every time it encounters a place in the syntax where, according to the notation, there should be a subterm, but there is none in the user input, it generates a fresh variable, puts it into this context u, and then treats that as the result of parsing in that position.
By saying there is none.
So let's look at an example.
Could I ask my question?
Okay.
Do you mean, when you say there is none, you mean there's just nothing there to be parsed, or is this something
there
already
is
where
nothing.
the user says, oh, well, like a do unknown or something?
So, you could also have an underscore for the user explicitly saying.
Okay.
So underscore counts as nothing in that sense. But there could also literally be nothing. So
I can.
we might have something like a term, you put it in quotes to say it's a string, which just says lambda x for an easy operation that has implicit arguments. Let's just say f x. And let's put an underscore just to be complete.
So f is binary.
And f is some notation that existed previously. Constant f with a notation of f2, 3.
And that's in C.
Sorry?
That's in C, or
Yeah, that's in the context C. So f expects 3 arguments, but the first one is implicit, it's not mentioned in the notation. And also the user has explicitly omitted this third argument to put in underscore. And the whole thing occurs inside a lambda, where the user has explicitly has omitted the type of the bound variable. In that case, our, let's see, maybe red boxes around the example. We will get a parse result where our u has 3 unknowns. They will be something like I think this would actually be called x1. And then something like I2, be the U, and the T will be, well, the actual syntax tree, which has the OM bind. I have to do this in Scala now. Running out of space, unfortunately.
I don't understand where exactly the U comes from, or what exactly the U means.
So the U is the context. It holds the unknowns.
Oh, I read content for some reason.
Ah,
Okay.
Yeah, my hand.
Because it looks like an N. And
Yes.
it doesn't look at all like an X.
If it says context, then okay, then it's more.
Yes.
Anyway,
A strange idea of what an X looks like.
No, that's the correct X according to how you learned it in school. At least
Maybe
I
how you
learned
learned
it.
it in school. Anyways,
Well, the way I learned it is, of course,
so
the correct way. Because it was in
to get
Bavaria.
back a context,
There you
containing
go.
the unknowns. Parser inserted.
start that sentence again, please.
We get back a context containing the unknowns that the parser inserted during parsing, and the term which is the result of parsing, using the unknowns in those places where the parser didn't find anything.
Yes.
And the local names are themselves a list of strings as a data structure in Scala. So we can have qualified names. And the convention is all the variables that MMT uses for itself start with the empty segment. So in Scala, technically, the name is empty, and the second name is X, and the third name is 1. So the
Okay.
slash separates the components of the local names. And I use an empty first segment to indicate the variables owned by MMT. So when you print it out to the user, those variable names start with a slash.
And are there any variables that don't belong to MMT?
Like the ones written by the user, like the X.
Oh, okay. Yeah.
So it's like a reserved namespace, everything that starts with the empty segment.
Yeah. Okay.
Then why is the X starting with a slash if it's written by the user?
No,
Is
this
that a
is the
different X?
unknown introduced for the missing type of X.
Oh,
I'm
okay.
just reusing the variable name to make it easier to read when you print it
Okay.
out for debugging.
Can you maybe call it X type or something like that so that it's clear?
Well, that's what it's actually called internally, I think.
Leave
Okay.
it like that. But can you explain why there's an X, an I, and an E? Do they have
So
any meaning?
I is for implicit argument, and E, actually I call it differently, I just forgot what I call it. I'm using E for explicitly omitted.
Mhm.
Implicit and explicitly omitted?
Maybe that's confusing. Let's call it gap, I don't know, or U for underscore.
What happened to the first argument of F? So F1, it doesn't occur in the notation. What
No, it
happens
does.
to it?
The implicit 2 is the first argument, X is the second, and the unknown 3 is the third argument.
Okay. Okay, I see. I was just confused that it said I2, but it's...
Right, so
We-
all the
I
unknowns are
want-
numbered to make sure they're all of unique names.
Okay, so they're numbered not with respect to their class, but globally.
Yeah, probably. I
Okay.
don't actually remember. The numbers just make sure everything is unique. So the parser found only 2 arguments, but the notation says, well, you only expect 2 because 1 is omitted. So that gave us a variable, the underscore gave an unknown, and the missing type here also gave us an unknown. So 3 unknowns, and they're inserted in the corresponding place.
So I have to still conform to the notation. If I remove the underscore, it would no longer be valid.
Yes.
Okay.
Yes. The notation says 2 arguments are coming, and you're only getting 1.
Okay.
Now, this is done for all terms. in particular for the type entity fenians. And now we have to check. For checking, we have to build a checking unit consisting again of a context, which is the same as the one that we already used for parsing. It's just the context which we're currently in. The unknowns, which have to be solved, those are of course coming from here. So, here's some blue. And then the judgment that we have to check. The judgment is really the main input to the checker, saying this is the thing that has to be checked to make sure the declaration is well typed. There's a couple of judgments. I've written the most important ones down here. We have the typing judgment. This is Scala notation now. So the classes really are called typing, equality, and inhabitable. They all take a context and then some terms. I've written the judgments again here in MMT notation that you would find in the paper, which is a bit easier to understand.
The paper.
So this is a normal typing judgment.
Which paper?
In any paper that you would write or that you would read about MMT. Or in your thesis, if it comes up, you would use something like this. But of course, in the implementation, you have alphanumeric names for them. This is the typing judgment. A term must be typed by some other term. This is the equality judgment. Two terms should be equal. And this is a less usual judgment. It's the inhabitable judgment, which means TP is allowed to occur on the right of the colon. You can think of it as TP as a type, except without any foundational commitment to what types are. So it's just something may have this thing on the right of the colon.
Yeah, but is there some foundational commitment to what equality means here?
Is it syntactic
I could
equality
actually
or
say that.
semantic equality?
So let's say built-in rules. We have EQ is congruence. Then alpha renaming.
What do you mean by EQ is congruence?
It's an equivalence relation, and it commutes with all the operations. In particular, so it's an equivalence, and we have if gamma TA gamma t equal t prime a equal a prime, then also t prime a prime, and if gamma t inhabitable and gamma t prime, then gamma t prime inhabitable. So there's nothing that can go wrong if you replace equals for equals, because they just always behave the same. So any question that MMT can ask, meaning any judgment you could pose, allows substituting equals for equals. If I have it for t and t is equal to t prime, I have it for t prime too.
And what is that? So gamma proves T inhabitable. What is inhabitable?
T.
So gamma proves T is the thing that is inhabitable?
Yeah.
Okay.
And it also proves that t prime is inhabitable if.
Yeah, the thing is it looks like a comma there between.
Yeah, I rewrite something.
No, that's fine.
And other than that, I think there are no built-in rules. Great.
I'm not very comfortable with inhabitable. What exactly does it mean that there's
We'll
a term
see in a
with this?
moment.
Okay.
Okay, so I'm sorry to harp on equality again. That is not just syntactic equality, but also some sort of semantic equality.
It's a binary relation on MMT terms. And these are the conditions that MMT assumes to be true about it.
could there be two terms that are equal that are not binary equal, say, like not the same exact tree?
Anything that is equal to an MMT must be interpreted as the same value if we have some kind of model.
So,
But you could have things that are semantically equal, but that MMT cannot prove to be equal.
so could we have a judgment that is true called the term 1 plus 1 is equal to the term 2?
Yeah.
Okay.
I forgot one more root definition expansion. If a constant has a definition, you may replace the constant with a definition, and that would also be equal. So every constant is equal to its definition.
Hmm.
And of course, every constant has the type that it has. There are some more judgments, but these are the most important ones. Now, while all terms are parsed in the same way, checking depends on where the term occurs in the abstract syntax tree. Most important example is you want to check a constant with the type and the definiance. What checking units do you build to check this constant? So let's say A and T are parsed as the following parse results with some unknowns and the actual terms that we parsed. First, we check the type, and to check the type, we check that it must be inhabitable. And I guess, let's take here. This must be a T. So we take the parse result T, check that it's inhabitable, and we provide the unknowns and the global context. The general idea of checking is that we get a check result containing a substitution which will be the substitution for the unknowns. Meaning checking will not only derive this judgment, but it will also find a substitution for these unknowns such that this judgment is true.
Will it find a substitution or the
The
substitution?
invariant is that there should be a unique substitution for the unknowns in U, such that after substituting into J, we have a true judgment.
There's a, is that an exclamation point for
Yeah,
unique?
for unique.
Yeah, okay.
Maybe I should bring this up. So we want, the idea is if there's more than one substitution, that means the input is ambiguous, so it's rejected as a mistake. Or if the solver cannot find a solution, then the input is also rejected as underspecified. So let's say we get a check result with some solution gamma for the unknowns. We will substitute in the T so that we now have a term that doesn't use the unknowns from U anymore.
Okay, that's a T in square brackets is what?
Substitution application.
Okay.
You can write gamma of T if you like. So the unknowns from U, which may occur in T, are substituted with the solution gamma, meaning every unknown is replaced with its substitution, and with its solution.
And
And
that's
then
supposed to be T prime as.
And then we check that this T prime, in which these unknowns U prime may occur, is typed by the expected type.
But there might be different unknowns in U prime, right?
Right, we have to solve these in the second checking unit, which gives us gamma prime for the unknowns that occur in T prime.
Yeah.
And then the ultimate result is that we have the declaration A. Well, I guess this should be. We take this term, substitute by gamma, take this term, substitute by gamma. That's the result that the checker will then return. Meaning the checker updates the declaration that after parsing looks like this into this.
Yeah, hang on.
Is the order because of the way we put the objects in MMT, or is it always first type then definition?
First the type so that you have it in order to check the definition. The idea is the definiant has to conform to the type.
Mm-hmm.
So you need to know the type to check the definiant.
So the order I write it in an MMT is
So
ignored.
that's irrelevant.
What happens if I have a constant with just a definition and no type? Does it insert
Right, good question. If you
one?
have only a type, then it's easy, just drops the second check.
Right. If I
If
only
you-
have a type, it's
Yeah.
not.
If
But
you
if-
only have definiants, then something slightly different happens, then it will try to infer the type of the definiants.
Which means it inserts one unknown for the type.
Exactly, it inserts one unknown for the type, and then checks T against that unknown type,
Okay.
in the process of which it will also figure out what the type is, and it will then
Right.
put the entire type in here. Yeah.
Okay.
So you can think of it as saying, you do the exact same thing, you just add an unknown type.
Alright.
And that explains pretty much the overall structure of the data that is passed around. The next step would now be to look at how does the algorithm do that. So how does the parser actually get from a string to this thing? And how does the checker actually go from a checking unit to get the substitution?
I can't help but notice that we do not have simplify on the board anymore.
Yeah, I figured maybe we don't have time, or maybe we don't get to it.
How much longer? When do you have to leave? At 5 sharp?
Yeah, a little bit more time.
Okay.
Well, but does it make sense to now open the whole can of worms and how things
I
do
think we
things?
can omit simplify for now. It's not that critical. It might be more interesting to say a little bit more about the algorithm.
Okay.
I'd be far more interested in parse than in check, but that's just.
I'm far more interested in check than in
Me too.
Yeah.
Well,
Let
then,
me just say one more thing. There's also constraints and errors.
You
So
arrows or
Errors.
Errors.
Okay.
So
Like mistakes, not as in both.
yeah, the checking returns three things: a solution for the unknowns, constraints that must be true for the judgments to hold, but which the checker couldn't actually prove. So you can think of the invariant as being all the conjunction of all the constraints implies the judgment. But the checker couldn't actually prove those constraints, so it passes them back to the user. That's
Cons-
usually a mistake.
Yes.
Right.
A
Okay.
constraint takes what form?
It's also a judgment, it's like a list of judgment. And the errors are when the checker definitely determines that something cannot be well timed. In that
So-
case, an error is generated.
the constraints, when I get a yellow squiggly line,
In
for example, I
JNF,
haven't proved uniqueness of something.
that usually means there's three things that can go wrong. The solution might not be total. There might be unknowns that couldn't be solved.
Mhm.
The list of constraints could be non-empty, which means there were conditions that the checker should have checked but couldn't.
Hang on.
Is there a
So-
solution in that case still?
Yes, because you might have partially solved the unknowns, and substituting those might help the user figure out what went wrong.
So first one solution is possible to not be total. Second failure mode was
So let's say success condition. This must be total. This must be empty. And this must be empty.
MMT always find a solution if the last solution?
You didn't. Sorry.
That's the
No.
invariant. What? Sorry.
There are many situations where a solution exists, but the system just can't find it.
Ah, okay. Ha, that makes me feel better. Anyway, I think you omitted the third one that you mentioned.
Which third one?
Nope. There's three things. Solution needs to be total, constraints need to be empty, and errors need to be empty.
Yeah.
Is it possible that there are constraints but we still have a total solution?
Yes.
Okay, good, then I got it.
You might have solved all the variables, but then there was some
Yes.
very difficult precondition that you couldn't discharge. You could also have a total solution and no constraints left, but an error.
Okay.
Like if you just have 1 equal 2 or something, then there were no unknowns to begin with, so this is trivial. There are no constraints left because the judgment 1 equal 2 was discharged by generating an error. So, what does the checker do? You know that there are typing rules for these judgments in principle. Some of them are built into MMT, some of them are supplied by the context. So the checker traverses the entire context and collects all the rules that it's supposed to use. And then starts, together with these rules, to try to check this judgment. And this proceeds as follows. You look at the judgment, and based on the judgment you determine which rule you can apply. Then you apply the rules bottom up, meaning you have a conclusion, and above the horizontal bar you have your assumptions. So you discharge the conclusion, but then you have new things you have to discharge. So what happens initially, the judgment to prove is in the list of constraints, the only one. And then you always take the first one from the list of constraints, find an applicable rule, use it to discharge, and then the premises of that rule become new constraints which you have to know checking.
Yeah.
If something disappears because you have closed the proof, then the list of constraints will eventually be empty. And now a problem can occur. You might not know which rule you can apply because you have an unknown sitting at the top of your term. If you're supposed to check a term against an unknown type, well, there's no way you can proceed at that point. So you may have to say, this constraint I can't handle now, I delay it. So you just put it back into this list at the end, and you go to the next one, and you hope that these other constraints that you still have, you'll eventually be able to solve the unknowns, so that when you come back to the other delayed constraint, you'll be able to make progress there. And then that's basically one big while loop that cycles through all these constraints, picks a constraint, sees if there's a rule that's applicable, if so, applies the rule, if not, puts the constraint back, goes to the next one.
And the rules are designed in a way that they simplify it always. To avoid that it
Ideally, yeah.
don't blow
It gets
up to
terminates eventually, yeah.
Yes, okay.
How do you make sure of this termination?
I don't. It's the task of the person who writes the rules to
Okay.
write rules that will lead to terminating behavior.
So if you encounter an unknown, delay.
And then sometimes you determine, you encounter a judgment where the solver is smart enough to say this cannot be true. Like 1 equal 2. Or if you have two bound variables x and y and they have to be equal, usually that cannot possibly happen. Yeah.
What if more than one rule is applicable?
Most of the time it's just the first one's taken.
Is that a smart idea?
Well, for most type theories there will only be one rule applicable if you tune your rules correctly. But yeah, that is something that we have to look into.
And then later it backtracks? Or?
You need backtracking, but it's tricky because you might try to use the one rule that may lead to a long chain of stuff where you solve some unknowns, and then later on you get stuck, then you have to backtrack all the way, like unroll all the state changes you made to the unknowns, and start over. So that's not implemented yet, but that's how you would have to do it.
You said it might not terminate. I've never encountered that.
Yeah,
So
the rules
because
are
it's
written
very-
in a way that this is very unlikely.
And what would happen? You
I
get
think Dennis finds some of those from time to time.
If you have subtyping, then of course what the rule does is it tries to prove subtyping. That's an open search problem. Then that's typically the source of non-terminating type checking behavior.
And does it throw you an error eventually when that happens, or does it just go on?
No, it just goes on.
It
Just
will probably throw an error whenever, and I'm guessing this is some kind of history tracking, which rules it applies. Eventually that's going to hit memory limit.
yeah,
And
and
then
then
you'd get a stack overflow.
Well,
Quite a few.
yeah, that one we would get.
but it's
But the arguments are kind of recursive enough, so maybe that doesn't even happen. I've never had a stack overflow during the type checking. But I have timeouts of the prover.
What do you mean by, so it does have a timeout, where it eventually,
You can set a timeout if it's up to the rule that calls the prover.
no.
Or that calls it with a timeout or without. While the solver does all this checking, it keeps a history. Every time it does something, it puts it into the history. The history is a tree, because every time it branches, it will also branch the history. Whenever an error is reported, the entire history from the beginning to the point of this arrow, so the branch on that tree, is stored together with the arrow, and that's what is shown in the ID. So, following the history line by line, you see which rules were applied, what the intermediate judgments were. Sometimes the judgment gets delayed, then the history picks up whenever the judgment is reactivated. Then typically between delay and reactivation, you will see that some unknowns have disappeared, because they were proved in between while this judgment was delayed. And then eventually it comes to the error.
In the output that has some sort of graphical representation with the different numbers of dashes, which I guess
Yeah, the
somehow
idea is that some nesting in the history is represented with dashes, and it should be looked over and cleaned up. I think it's not always as intuitive as it was envisioned.
I think probably due to the delaying of stuff.
It can be that during the delay, the indentation tracking gets messed up. We should look into that. Now, unfortunately, there are very few things that we can be certain are ill-typed judgments. Why is that? Well, the most important rule is the application rule in the LF type theory, which is something like you want to check something like F applied to A against some type B. You've already inferred that F has type A to B, and you've inferred that A has type A prime, and now you go into a check of A equals A prime. So this doesn't belong to anywhere. So let's say the rule works like this. What you see is checking the A might not fail. This is usually the typing error that you would hope to find if you have a bug in the A here. That you get a message like expected uppercase A found uppercase A prime.
And then you would expect it to say, these are not the same, but what the
Yeah.
solver actually does is, oh, maybe these are the same. Let's try to prove that. And-
Exactly.
Yeah.
Because we have an open world where users may add arbitrary equality rules, or to check and as well, apparently the user assumes or knows that A and A prime are equal. So let's see if I can how to check that. And then will you apply equality rules to make sure that these two are equal. And eventually it will find that it will have simplified these expressions so much that they are stable. Stable means they cannot be simplified in a way that would change the top level symbol. And then both terms have different top level symbols. Then it will eventually say these terms have different shape. They
Oh, yeah, I
cannot
know
be
that
equal.
one.
Yeah.
And that's the error message that you get almost all the time. That's pretty much the only situation where an error is generated. And then usually it comes from the fact that further down the history, there was a function application rule applied, which introduced an expected type for a specific subterm, which didn't obviously match the inferred type, and the system proved, or tried to prove, equality of those two types, until the types were simplified enough to be stable, at which point it concluded that they cannot be equal. So at that point you usually have to scroll up the history until you find the place where it actually tells you the typing judgment that it's trying to establish. That will be in the history further up, and there it will say something like, I inferred a function type A arrow B. Now I'm going to check that the inferred type is equal to the expected type, and then you see further judgments coming up that will discharge or try to discharge the equality. Some work would be helpful to improve the error messages,
Mhm.
make them more intuitive to users, but it's quite tricky with all the delaying and so on.
Is the equality on types A and A prime modifiable by the user?
Yes, these are terms just like these. So left and right hand side of the code are just MMT terms, and they're treated the same way by MMT. So users can add rules for anything, including equality of terms, and that means equality on the left or the right.
So I can also add custom rules for inhabitability.
Yes, and in fact we do that. For example, for LF we say everything that is of type is inhabitable. So in LF the rule would be if A is a type, then it's inhabitable.
And the user can add these, right? Not just
That's
like...
what the user adds in the case of LF. Just like the user adds this rule.
Yeah, but this is not baked into MMT itself.
No,
so
this is
very
part
user-
of the
Yeah, very good.
the LF definition. LF has two of these rules. The other one is if A is a kind, then A is inhabitable.
What's a kind? In
Kind,
That's something else
type, in
specific.
particular type itself is a kind.
Ah, okay.
So this legitimizes declarations of the form A colon type. Because you're going to check inhabitability of this thing. So you get into this position, you say, oh yeah, A is colon kind, done. And this rule legitimizes things like C colon A.
Ah, okay.
Where you say, A, I know A is a type, okay. Then with this rule, A is also inhabitable. So these two rules are the rules for inhabitability that we need to get LF behavior.
But
Mhm.
only
What's the intuition behind inhabitability?
Sorry?
What's the intuition for inhabitability?
It's legal to have it inhabited by something. Inhabit means a term inhabits its type.
But isn't that true for any type?
Yeah, that's what this rule says. Any type is
But not,
inhabitable.
like 4 is not inhabitable. Or,
That's the number 2, yeah. It's not inhabitable.
so it's for all types,
Yeah, okay, yes, yeah.
but
yeah,
not
yes.
everything is a type.
Not every term can be considered as a type.
Yeah.
Yes.
And it's up to you which ones are.
Mm-hmm.
And you might have some tricks in there. Let's say you have a set theory where you say set colon type. Clearly set is inhabitable because that's what this rule already says. Maybe later on you have nut colon set. And normally in LF, nut is now at the lowest level, just some expression. It's not going to be inhabitable. But MMT wouldn't mind at all if you say, oh, I want a rule that everything that's set is also inhabitable. Then you can add that rule. It won't be LF anymore. It will be your variant of some kind of set theory out there.
Okay.
That makes sense.
So just syntax-wise, inhabitable is it comes with LF, I assume.
Kind of. This is baked into MMT. Like these are primitive operations of MMT. These three judgments. But then which things are inhabitable, that comes with the specific type theory.
Yes.
Built
So
inside.
I would in the syntax really write a inhabitable, or what is the syntax?
No,
word?
these rules are written only by language designers who use MMT to build languages.
Yes.
So that's what I did for LF and what Dennis is doing for the LFX languages.
Yes.
But usually you do that very rarely.
Yes.
And once you've done it, users, like the role that you're in at the moment, never see these rules at all. They just
Yes.
write these declarations. And then MMT under the hood will check that A is inhabitable. And that will mean it looks up these rules.
So, is there a way to write these rules in surface syntax, or is it Scala?
No, these rules are always implemented as Scala snippets.
Ah, okay. I thought that
Yeah.
that basically in the row theory LF or something
No.
in MMT you find that
They're
word.
written as Scala snippets and they're linked into the theories just by their name.
So
Okay.
if one were to implement type coercions, one would need to add a surface syntax for some of that.
What kind of coercions would you want?
For example, that the inner product of x with x itself is a real number. Usually it's a complex number. So I'm sorry if that's not.
Yeah, that's something you can come up with. You would probably have to write some of these rules, figuring out how the subtyping works. You can talk to Dennis about that. You can go into more detail.
One thing I could imagine is C-like type conversions, where you say something of the shape, or Scala as instance of. If you want, you could implement a rule of that which says as instance of st is of type T or something.
Yeah, so in
like
general we need something like that.
that. Yeah.
We need better subtyping support and better subtyping would also be a judgment here. I want to list that.
I think you probably want a rule just for debugging to be able to turn off typing for a single subterm somehow. So that you can tell, okay, I know this doesn't type check yet, but does everything else work if I force it to be?
Possible.
Just for debugging, I'm saying
Yeah.
you never want this in your end result, but during debugging you want to be able to say, does the rest work?
So that's the basic overview. The next session would be about the actual details of the algorithm. But if you have the intuition, that goes a long way.
Yeah.
Just do the usual type checking by applying the rules as they are applicable. What I haven't shown you is yet how to solve the unknowns. But well, eventually you're going to have a judgment where it's like unknown x should be equal to this term t. At that point you say, well, okay, I'm solving this judgment by making t the solution of the unknown. That's sufficient and necessary for the judgment to be true.
Mm-hmm.
Then that usually comes from here. So once you go down the derivation of this equality, eventually you're going to be able to solve unknowns because they have to have a certain value for such an equality judgment to be true.
Yeah.
And that's how the unknowns get solved.
Can you show two different terms which cannot be made equal? where MMT can see that?
Yes, that's when the top level symbols of the terms differ. So if you have something like C of something, D of something,
That's types have to, or terms have different shape, thus cannot be equal.
But can we have a definition for D?
that's it. The simplifier is called on both terms, and if
Ah,
all
yes,
simplification rules say, I'm unable to change this C here.
Mhm.
In the other case, all rules say I'm unable to change this D into anything.
Okay.
And neither C nor D has a definition. Then the terms are considered stable.
Okay.
And for two stable terms, if the top level symbol isn't the same, there's nothing you can do, and then you report.
I must say this architecture of allowing the user to add rules to the simplifier is pretty clever actually.
Yes.
I like it.
So I haven't shown that in detail. The simplifier works similar to the checker in the sense that it uses all the rules that are available in the context. And you can also supply your own rules, and there we do have a surface syntax. You can add rewrite rules directly from NF.
Yeah, that's maybe something for next session.
Yeah, and that means you can arbitrarily customize the equality relation, even in undecidable ways. And that's something that most systems don't have. And that's why checking an MMT is so hard. If you have a closed world where you know exactly what rules you have, and
Then you
know
can just
exactly
use all
what
of them.
terms you have,
Yeah.
that's what happens in the programming language. If you know exactly what constructors your programming language has, then you're able to do certain arguments where you quickly determine that two things cannot be equal. But an MMT has to exhaustively apply rules before it can conclude that. I think I should go now.
Okay, thank you again.
Thanks.
We'll try to have a halfway decent write-up of this by the time we do the next session in January, I think.
Yeah.
I think it's also a good kind of point anyway, saying now we go into concrete worlds.
Yeah.
Sorry, what?
Now we go into concrete worlds away from
Yeah, one could
empty
show the
stuff.
NF rules
Yes.
in the next
Yeah.
session, and we can also look at the parser a bit more. It's relatively straightforward.
Yeah.
Orders the notations by precedence,
Yeah.
and then it matches all the notations where it can.
Yeah, we have
And picks the one with high
just
precedence.
added a few sentences.
No, it takes all the ones with the lowest precedence,
So here this
Oh,
one
yeah.
is, and then
matches them wherever it can.
also scribbled some.
Oh,
Okay.
yeah.
It introduces certain substrings, which it knows to be
One term.
one term, yeah. And then it recurses into those with all the notations of higher precedence.